Alright, so in this video we're going to be looking at a quick way of doing integration by parts. So to start off, what is integration by parts? It's basically a way of undoing the product rule when integrating. So the way to show that, we'll just start out with the product rule, which is that the derivative of a function u times a function v is equal to the derivative of u times v plus u times the derivative of v. So from there we can do a little bit of rearranging so that we have u v prime equals the derivative of uv plus u prime v. So then we can integrate both sides, which will give us the formula for integration by parts, which is the integral of u v prime dx is equal to uv minus the integral of u prime v dx. So that right there, that is the formula for integration by parts. So what this is saying is that if we have a function that we're trying to integrate where one of its factors u we can differentiate and the other v or v prime we can integrate, then that is equal to uv minus the antiderivative of u prime v. Just to show this with a simple problem, so the integral of x times e to the x dx. And so generally when you have x to some power, that's a sign that that should be the function that you differentiate. So the x right here will be our u, and then that means the rest of it, which is the e to the x, that will be our v prime. And so if we look at this formula, this will give us, so u is just x, and then v, that's the antiderivative of e to the x, which is still e to the x, minus the integral of u prime. So the derivative of x is just 1, so just 1 times v, and we already said v was e to the x. So the antiderivative of x times e to the x is equal to this. And then here the antiderivative of e to the x is just e to the x plus c. So this is all equal to x e to the x minus e to the x plus c. So that was easy enough, but there are other problems. For example, if I had the integral of x squared sine 4x dx. And so once again we should just make our power of x the u, so we can differentiate that. But if we differentiate this once, that'll give us 2x, but then we have 2x times a trig function, and we still don't know how to take the antiderivative of that. So we can do that again with the integral that results, which could give us an integral that we can do. And for this one, you'd actually only have to do that twice, so it's not too bad. But say you had a power of x like that was really big, like x to the 10th, then you'd have to do that 10 times, which you'll probably realize would take a very long time. So instead, there's this method of integration by parts called rapid repeated integration by parts, or it's also known as tabular integration. And so the way that works is, so you have your u and you have your v prime. So we want to make this our u and this our v prime. So u is x squared, v prime is sine of 4x. And then so what we want to do is differentiate this side over and over again and integrate this side multiple times. And so when you have a power of x, really what you're trying to do is just differentiate it until you reach 0. So let's see, x squared, derivative of that is 2x, and then the derivative of that is 2, and then derivative of a constant 0. And then on the right, so we can do u substitution, but let's just think about it. So if we were to take the derivative of sine of 4x, we would take the derivative of sine, which is cosine, of 4x, and then by the chain rule multiply it by 4, and we would do that each time. So if we go backwards from that and integrate, we would take the antiderivative of sine, which is negative cosine, and then divide this thing by 4. So that would give us, so we have negative cosine, but then divided by 4, so negative 1/4 cosine of 4x, and then we do it again, so antiderivative of cosine is sine, divide 1/4 by 4, negative 1/16 sine 4x, and one more time, antiderivative of sine is negative cosine, the double negative cancels out to make a positive, so divide this by 4 again, 1/64 cosine of 4x. And so once we have this kind of table done, what we want to do is draw a diagonal like this. So the first entry on the u column goes to the second one in v prime, and so on until here, and then you do a horizontal line from the u to the v prime, and then you start with the positive sign, and you can alternate. So what this is telling us is that the antiderivative of x squared times sine of 4x is equal to, so basically what the sign tells you is whether to subtract or add. So all this is equal to, so what we're going to do is multiply across the diagonals. So x squared times negative 1/4 cosine 4x, that would make negative 1/4 x squared cosine of 4x. And then here we have 2x times negative 1/16 sine of 4x. We have a negative, so we want to subtract that. And since this is negative, that gives us a positive. So this gives us plus 1/8 x times sine of 4x. And then we have 2 times 1/64 cosine 4x. This is positive, and we're adding that, so you have a positive sign here, so that would be 1/32 cosine 4x. And then the last part, 0 times that, that's 0. When you get to this last part, what you do is you take the integral of this side multiplied by that side. And so here we just have the integral of 0, which is just a constant, so plus c. And there we have our antiderivative. And so you can see rapid repeated integration is much faster than just doing it all by hand. And so here it was pretty clear where to stop. Like, you know, if you had a power of 2 that you're power of x that you're differentiating, you just do it till 0. But here's an example that might not be quite as obvious. So the antiderivative of natural log of x. So it's probably not too obvious what to do with this because it doesn't even look like a product of two functions. But really, if you think about it, what this is the antiderivative of 1 times the natural log of x. So we can use that as our product. So we'll write our u v prime over here. So again, it's tempting to use 1 as our u because, you know, you differentiate that once, you get 0. But remember, that means that v prime would be a natural log of x, and we obviously can't integrate that. That's the whole point we're trying to use this for. So we'll have to make natural log of x our u, and we'll make 1 our v prime. So remember, we differentiate on the left, so derivative of natural log of x is 1 over x, and then the antiderivative of 1 would be x. And so here again, there's no clear place to stop. You're not going to just hit 0. And so what you need to do in these cases is just look at the u and the v prime in the bottom row and see if you think you can integrate that, and if you can, then you can just stop there. And if you don't think you can, just go one more and just keep going until it looks like you can integrate the product of the bottom two functions. So if we stopped here, we would have a diagonal going like that, and then horizontal like this with a negative. So natural log of x times x, so x natural log of x minus the integral of 1 over x times x, which is just 1, so the integral of 1 dx. And so the integral of 1 dx, we know that's just x, so that's it. We don't have to do any more repeated integration by parts. This is all equal to x ln of x minus x, and then of course plus c. So there. is our antiderivative. Here's another problem. This one's definitely a lot trickier. And so here it's pretty clear what our product is. And of course, you see the x cubed, you might want to differentiate that, but we don't immediately see a way to integrate e to the x squared, right? What we can do actually is use a bit of u substitution, and you might go, how do we do that? Well, first we will rewrite this integral to be the integral of x squared times x. So that's the x cubed right there. We can read it like this, and then e to the x squared dx. So here might be a bit more clear. So if we were to use u substitution, we would make our u equal the x squared, and then we can see our u would not only show up here, but also here. And then du would be 2x dx, and because we have just an x and not a 2x, we'll take half of that, so half du is equal to x dx. And so now we can rewrite this whole integral in terms of u. So we have half du right here, so we can bring out the half. Half times the integral of, so x squared here, that's u, so u times, and then x dx, that's the half du, and then e to the, so this would be e to the u du. And then this is something that we can now use integration by parts on. So we get u v prime. And keep in mind this u and that u are different. Could have used a different variable for the substitution, but whatever, just keep that in mind. So our function u would be our substitution variable u, because this can just be differentiated twice to get 0. And then v prime would be e to the u, since we know how to integrate that. So this would become 1 and 0. And this would just be e to the u, because antiderivative of e to the u is just e to the u. We draw our diagonals and the horizontal lines, so start with a plus and then minus, plus. And so here, this all is equal to half out here times, and then u times e to the u minus e to the u, and then here plus the antiderivative of 0, which is just a constant. And now we can substitute x squared back in for u, which would give us half of x squared e to the x squared minus e to the x squared. And then half times a constant is still a constant, so plus, so we can put the plus outside. And there we go. That is our answer. And so I have one more problem, and this one's definitely going to be the hardest one that I've shown in here, but the antiderivative of cosine squared theta d theta. And so right here, cosine squared is just cosine times cosine, so we can use integration by parts, u v prime. So both of these in this case are going to be cosine theta. And so let's try doing integration by parts once. So the derivative of cosine of theta is negative sine theta, and the antiderivative is just sine theta. And so let's draw diagonal. That'd be plus, that'd be minus. So what this is telling us is that the integral of cosine squared theta d theta is equal to cosine theta times sine theta minus the integral of, well, this is negative sine squared theta, so the double negatives cancel out, so it gives a plus integral of sine squared theta d theta. And so right now it's probably not too clear what to do with this integral, but remember, by the Pythagorean identity we can rewrite sine squared in terms of cosine squared. So this is integral of cosine squared theta d theta equals cosine theta sine theta plus the integral of 1 minus cosine squared theta d theta. And so we still have a cosine squared theta in there, and you'll see what we do with that in a moment. But what we can do is, I'll write all this again. Antiderivative of cosine squared theta equals cosine theta sine theta plus, so we'll integrate both of these terms separately. So the antiderivative of 1, that's just theta, minus the integral of cosine squared theta d theta. And so now you might see the reason I actually wrote all this integral of cosine squared theta out to the left when I didn't really need to. It's because now you can add that integral to both sides, which will get rid of this. That gives us 2 times the integral of cosine squared theta d theta equals cosine theta sine theta plus theta. And now finally we can just divide both sides by 2, which will give us our final answer of integral of cosine squared theta d theta equals half cosine theta sine theta plus theta over 2. Rewrite that, theta over 2 plus constant. And there we have our final answer.